Friends, welcome to the set of lectures under module 2. In module 1, we discussed about different structural action of offshore structures. We also discussed about conventional environmental loading that act on offshore structures. We understood how to estimate the environmental loads act on offshore structures like wave load, wind load, current load, etc., using classical wave theories as well as power spectral density function or different spectrum. We then paid attention in the first module to that of estimate of dynamic response of structural systems under special loads, where we spoke about earthquake loading, ice loading, extreme waves, distinctly high sea waves, springing wave loads, ringing wave loads, etc. We have understood how to model these special loads that act on offshore structures, what could be the return periods, what could be the probability of uncertainty associated with these kind of loads, and what could be the consequences caused by these special loads on offshore structures of different variety and structural form. For our understanding in case study, we picked up compliant structural systems like, for example, a tensionless platform, and understood how the consequences of these special loads can affect significantly the degrees of freedom responses of these kind of compliant structures under the special loads. Now, interestingly, we need to also shape up our understanding on the tools related to structural analysis when such members are subjected to special kinds of loads. So, in module 2, we will pay attention to some advanced methods of structural analysis under special conditions, so that we know how to analyze the systems or how to get the stresses and bending moment, shear, etc., acting on the cross sections under these kind of special loads, but not necessarily the speciality arise from the kind of loads, but they arise under different other circumstances which we will discuss in this module. Under this module, we will first talk about unsymmetrical bending. We know generally structural members like beams, columns, etc., are generally idealized as one dimensional members. If you take a beam of a rectangular cross section, the length of the beam is so large compared to the cross sectional dimensions of the beam. So, we idealize this as one dimensional member. Each member has generally preferably axis of symmetry or at least one axis of symmetry, the intersection of which will be the center of gravity or the mass center of this body for any given cross section. If the load is applied on this, it is very comfortable and easy to compute the stresses in the cross section if loads are applied at prefixed points, or I should say planes. Generally, so far in all structural analysis of a classical methods, it is assumed that bending takes place parallel to the plane of applied moment. If this statement is true, then obtaining bending stress by a classical theory of m by I into y from the flexural equation is easy and convenient to apply. But in many cases this statement may not be true. Let us take a beam subjected to a bending action of this, which will make the beam to bend this way, which forms tension because elongation of fibers on the top and compression because of contraction of fibers at the bottom. If you cut a segment and take a layer at a distance, y from the neutral axis, let us say this is my x axis and this is my y axis, and the applied moment is m z. One can easily apply the conventional bending equation to find the bending stress caused by the moment m z. To be very specific, we should then say sigma x by y can be m z by I z z, which is also otherwise equal to E by r. So, interestingly, a typical cross section of any form will have the z axis, will have the y axis as marked here and subjected to m z, and that is the mass center of the body. So, obviously, one can now say that in the above figure y axis actually represents the trace of plane of applied moment. Whereas the applied moment is actually m z. Therefore, moment is assumed to be applied causing bending in planes parallel to the plane of applied moment. Under this condition, we can then say bending moment about y axis is said to be 0. Mathematically, algebraic sum of moments about y axis, which can be given by sigma x dA is then said to be 0, which amounts to, interestingly, an equation which says integration of z by dA should be set to 0, which will be true only when z and y axis are principal axis of inertia. Therefore, for symmetrical bending, we have the following observations. It is essential that the plane containing one of the principal axes of inertia plane of applied moment and plane of deflection should coincide. Second, it is therefore obvious that neutral axis will coincide with the other principal axis of inertia. That is a standard case which generally happens in almost all members which are assembled to become a structural configuration. But in the case of unsymmetric bending, in the other cases, when trace of the plane of applied moment does not coincide with any of the principal axes of inertia, then this type of bending is called unsymmetric bending. It is also otherwise called as uniplanar bending. In this case, non uniplanar because it is unsymmetrical. Therefore, under such conditions, in unsymmetric bending, neutral axis is no longer perpendicular to the trace of applied moment plane deflection curve is also not a plane curve. In the plane of applied moment. So, this complication will lead to non-usage of standard theory to obtain the bending stress. So, bending stress cannot be obtained by a straightforward equation of flexure as you see in this part. So, the complications will now come to estimate the bending stress because neutral axis is no longer normal to the trace of applied moment, and we all know the distance of extreme fiber is measured from the neutral axis normal to that, and moment should be on the trace of the applied plane and I should be with respect to the axis of bending. So, all these complications will now add up to estimating the simple bending stress, which cannot be now obtained by the standard equations of flexure. Let us ask what would be the consequence of unsymmetric bending. First, neutral axis is not perpendicular to the trace of applied moment plane members or cross sections which are not symmetric about vertical axis and also thin sections undergo twisting under transverse loads. Let us see how this particular consequences are important for members in offshore structures. Interestingly, in offshore structures, people use thin walled sections. The reason being, we need a member may be circular in shape, with large diameter to enable good buoyancy force, less thickness to make it weight lesser, so that installation, fabrication, constructability, decommissioning all becomes easy and simple. So, obviously, we are dealing with sections which are thin walled in nature. If the plane of bending does not coincide width of the applied moment, we always have unsymmetrical bending cases. Therefore, estimating bending stresses in such cases under special loads as well as nominal loads will be tricky. Let us take up examples of cross sections like I, angles, channels, which are generally used to support the deck the upper deck, the serviceable deck, service deck, cellar deck. For example, deck may be a plate of some thickness. You need to support the deck because they have larger spans, cross beams, columns, and another deck. Maybe the deck is supported with a lattice truss girder, etc., where a platform may be constructed to have all arrangements like a flare boom, like a drilling derrick, etc. So, when these members which anyway have two axes of symmetry, but if the loading is not applied or the plane of loading is not parallel to either one of them, or it is applied with a small inclination to any one of the planes, alpha maybe even 1 degree, the estimated bending stresses or computing neutral axis position to estimate the bending stresses is not simple. It is complicated. We need to understand the analogy behind estimating the bending stresses by locating the principal axis of inertia and then locating the position of neutral axis and then measuring the distance of fibers required to estimate stresses with respect to neutral axis along the principal axis of inertia to get the bending stresses. It is also observed that even a small inclination of 1 degree of loading, which can happen accidentally in a given construction practices in offshore structures, can cause a good hike in the bending stress, which can be as high as 25 to 30%. We will take an example and demonstrate this later. Now, let us try to understand systematically how to find the bending stress in case of unsymmetric bending. So, the objective is to find the bending stress at any point in the cross section we already know that in case of unsymmetric bending, moment will cause bending about both the axes of inertia. So, without locating these principal axes, one cannot estimate the bending stresses. Let us take a beam whose cross section may be of any shape, which has got axis z and y. Maybe we will put z slightly inclined. Let us say this is my x axis. I have now a principal plane u which makes an angle alpha with z. Let us talk about this plane which is the XU plane. So, the hatched plane is XU plane. This plane is plane of symmetry for a simple reason. The cross product of u v is set to 0, where u and v are principal axes of inertia. So, when you are able to locate these principal axes of inertia, then one can use the conventional flexure formula to estimate the bending stress. But if the load acts on zx plane, it becomes unsymmetric. If the load acts on zx plane, then it becomes unsymmetric. So, one cannot use the conventional equation of flexure to obtain the bending stress. So, what one should do in that case? So, the first step obviously will be to transform the problem of unsymmetric bending to uniplanar bending. How to do this? To do this, one need to locate the principal axis of inertia. So, the problem is now originated to a simple start saying for a given cross section try to first identify the principal axis of inertia. So, let us take a cross section of any shape. Let us mark the axis as Z and Y. Let us take any point whose elemental area is dA. Now, I want to locate two axes which is U and V. At an angle alpha from Z. So, interestingly alpha is measured in the positive V coordinate, okay, that is the sign convention we are following. In that case U can be given by Z cos alpha plus Y sin alpha, because U can be then resolved as Z cos alpha and Y sin alpha, whereas V will be the opposite direction. So, minus Z sin alpha plus Y cos alpha, because we know if this angle is alpha, this is also the same angle. So, Y cos alpha and minus Z sin alpha, we call this equation number 1. To estimate the bending stresses, at any point in the cross section, one need to calculate the moment of inertia, which is the second moment of area about UU and VV axis. So, from the first principles IU is integral over the entire area, which is V square dA, which can be said as integral for the entire area. V is taken from equation 1. So, minus Z sin alpha plus Y cos alpha to the whole square of dA, which can be integral Z square sin square alpha plus Y square cos square alpha minus 2 ZY sin alpha cos alpha dA for the entire area A, which can be written as sin square alpha, take it out because there is not going to be a variable over dA, integrate for the entire area Z square dA plus cos square alpha entire area Y square dA minus 2 sin alpha cos alpha is sin 2 alpha entire area Y Z dA. Z square can be now said as I y sin square alpha. Please see this figure. Z is the horizontal axis, z is the horizontal axis, z square, the second moment of area, will give me y. So, z square will give me I y plus cos square alpha I z, because y square will give me I z, minus this is product of moment of inertia, which is sin 2 alpha. We also know cos 2 alpha is 1 minus sin square alpha. It is also equal to cos square alpha minus 1. So, let us substitute in the above equation. So, we now say I v, sorry, this I u I u is equal to I y by 2 1 minus cos 2 alpha plus I z by 2 1 plus cos 2 alpha. I am substituting these equations here, minus I y z sin 2 alpha, which now gives me I y plus I z by 2 plus I z minus I y by 2 cos 2 alpha minus I y z sin 2 alpha. So, I can rewrite slightly I z plus I y by 2 plus I z minus I y by 2 cos 2 alpha minus I y z sin 2 alpha, which is my I u. Equation 2. Similarly, I v can be expressed as integral over entire area u square dA. Now, u can be seen from this equation as z cos alpha plus y sin alpha. So, integral A z cos alpha plus y sin alpha the whole square dA, which can be z square cos square alpha plus y square sin square alpha plus 2 z y sin 2 alpha dA, which can be now separated as cos square alpha area z square dA sin square alpha area y square dA plus 2 z y sin alpha cos alpha plus sin 2 alpha area z y dA. We already know that this can give me I y, and the second integral can give me I z, and the third integral is I z y sin 2 alpha. Substituting cos square and sin square in terms of cos 2 alpha, we can now say 1 plus cos 2 alpha of I y by 2 plus 1 minus cos 2 alpha I z by 2 plus I z y sin 2 alpha, which will now converge to I z plus I y by 2 minus I z minus I y by 2 cos 2 alpha plus I z y sin 2 alpha, which I call as equation number 3. Interestingly, adding equation 2 and 3, we get I u plus I v is I z plus I v. So, friends, we will proceed further in the next lecture of estimating and locating the neutral axis and bending stresses with some examples. So, we have now realized and understood in this lecture that unsymmetric bending is an important application in any structural engineering problems. Nevertheless, it is important in members in offshore structures. Let us understand the analogy behind estimating bending stresses when they are subjected to unsymmetric bending. Thank you.